All right, 9 o'clock. We can start. People online, if you can hear me, please say something.
Good morning, Professor.
Right,
Good morning.
thank you. Good morning. So, most people are online today, I can see. Like the weather's cold, so you don't want to leave your warm bed. Yeah. All right. So today we have, we'll do just a quick review question, some practice with interest rates from what we were talking about last time. I'll say a little bit more about that. And then we are getting into our preparation to do calculus stuff. So some various tools and things we'll have to recognize about polynomial functions. We'll say what those are and some things that we should know about them. And we'll probably spend our next class as well kind of reviewing more of those ideas, and then soon-ish we'll get to the actual calculus stuff. Also, the preview question that you did about sort of the curve, total revenue, total cost things, we'll talk a bit about that and how exactly those things can happen. So that's our plan. Just jump straight in with the interest stuff. First, let's see if we remember those two formulas that we talked about. Simple interest, what is our formula? AT. 1 plus I times T. All right, what is AT?
Time.
T is time. What is AT?
Final value.
So the kind of final value after T years. What is P? Okay, the starting value of the loan or the investment, whatever, the principal. That's our principal. And what is the I here? All right, interest rate. Interest rate. Remember, we have capital I, which is the dollar value of the interest that we are paying. That's quite different from the interest rate that's applied to the principal. The interest rate produces the actual interest. Compound interest, similar formula, but some part of it is different. 1 plus I. Okay, exponent T. All right, close the brackets first. So P times 1 plus I, then to the exponent T. Putting it outside the brackets is very important there. All right, so, and just to remind you, this is for when we are compounding interest annually. So once a year, the gathered interest gets applied back to the existing value, and then new interest is applied to the principal plus that extra interest. So happening once a year. After our practice question, I'll show you, just if you're curious, what the formulas are in these two cases, but that's not something that's part of our class. We'll just kind of quickly show you what those look like. All right, so those are the two formulas. So put them to use here. Two questions, try to calculate the values of these things. If you're online and you have the answers, you can write them into the chat. Okay, it's been 3 minutes. Let's talk about these. I don't know that anyone's finished, but I think you finished most of the question, hopefully. First one here. What information have we been given? Okay, interest rates, again, careful with that. So that is our I value. What else have we been given? Time, okay, so 3 years. And what else? The principal or the final value?
Final value.
Okay, they're saying final value. So we should read the question carefully. Look at the phrasing that they use. So present value of something, present value is a bit ambiguous, but expected to be worth this much. That's the future value. So present value therefore means the principal. So we are looking for principal here. And we have been given value after 3 years. 6,000, we've been given time, 3 and interest 7.5%, so 0.075. So there's the information. We just put it into the formula and there we go. So 6,000 equals P times 1 plus 0.075 times T, 3, and just rearranging here. 6,000 is equal to P times 1.225. So P is equal to 6,000 divided by that, 1.225. And as I mentioned before, probably gonna need a calculator to do the last step there. People were telling me in the chat, approximately $4,898. So there's some decimals that we're leaving off. We'll just write it as an estimation for now, or rough number. Okay, that's the first one. Second one, what information have we been given and what are we looking for? Okay, so we're looking for interest and we've been told everything else. And the other parts are pretty straightforward. So principal is 2,500 and the final value is going to be 4,875 and time is 8 years. So we want interest. So just put all the parts in the formula. 4,875 is equal to 2,500 times 1 plus I to the exponent 8. And we rearrange 4,875 divided by 2,500. All right, 1.95. So that's equal to 1 plus I exponent 8. And we take the 8th root of each side, 1.95. 1, let's just write the -1, same step. -1 will equal I. 8th root of that thing, that's not very fun to calculate by hand. Yes, that's what we were given. So that will be 1.087 and some decimals, and then subtract 1, and we get our value there. So 0.087. So again, approximately, because there's a whole bunch of decimals here. So that would be 8.7%. So if this is the investment goal, we have this much money, we want to reach this much final value, we have this many years, we need to find an investment plan or whatever that gives us at least 8.7% in order to hit that target. Okay, so 2 formulas, just put in the numbers. In our last class with the compound interest formula, let me come here. With the compound interest formula, we had examples where we solve for the final value and solve for principal, and we've just done this one where we solve for interest rate. It is also possible to solve for t, the exponent itself. To do that, though, we need a tool called logarithms, which are a bit beyond kind of the scope of our class. I don't have time to teach them to you like fully properly. It is possible. It's a button on your calculator that will let you do it. This is an example question about that. I'm not going to do it in class. I did this in the workshop last week. So if you're curious and want to know a little bit about logarithms or how to solve for t, we did this example there. But I'm not going to do that example in class. So these are the formulas. The compound interest one here, there's a slightly more complicated version of it. If we are compounding n times per year, often compound interest is not compounded once a year, but maybe each quarter or each month. And then, okay, but each month then our n is 12 or something. If you have a loan for a house or something, often that would be compounded once per month. There's also this other one where the compounding just happens kind of continuously, sort of infinitely. It's not just once every week or whatever. So there's another formula that will cover that. And it has this E thing in there, and that's another thing that's a bit beyond the scope of our class. We kind of need some calculus stuff to really understand what that is. But also, hit the button on your calculator if you're curious. Okay, so the top 2 formulas, these are the ones I'm expecting you to be able to work with. The other 2 are just for your curiosity. A finance or accounting class will go into a lot more detail about those and all the different things you can do with these formulas. Okay. Anyone have questions about interest stuff from the previous classes or anything? All right, so slopes. So this won't take too long. I showed your section a little bit of this last time, but as I mentioned, for doing calculus, it's really important that we can visually just quickly identify what a slope is approximately. Not the exact number, we have calculus tools to do that for us, but approximately what the slope is. If we can't see that, then it's going to be really hard to understand what calculus is helping us with. So let's just, for sake of consistency here, let's just go through this again. This first one here, Is this a positive slope, negative slope, 0, or undefined?
Positive.
Positive. The next one. This is a slope of 0. It's perfectly flat, so no slope there. What's the next one? This is negative. What about this last one? Okay, so this is our undefined slope. So that part should be instant. Everyone should be able to recognize that right away. What, for this first one, the slope is what number? 1. Okay, so that's a positive 1. We can recognize that because this is a 45-degree angle, perfect 45-degree angle. So slope will be exactly 1. Here, again, 0. And this third one, negative 1. So again, 45-degree angle, but going downward. So that's the slope of exactly negative 1. You should be able to recognize those quite easily. Then we can just extend that to recognize the things that are between those positions as well, which also shouldn't be too bad. So let's say this one here, this second blue one. So is this positive or negative? So it's positive, just like the other one, positive. Sorry, let me, yeah, right. Slope formula, delta y over delta x. If the change in x is always the way that we think about these sort of moving to the right. So the change in x is always positive. So it's just about the change in y. So if it's going up, change in y is positive. So that will be positive. What kind of positive number do you think we're dealing with here? Very large number, very small number? 1. Okay, so if this is 0, sorry, if that's 1 and this is 0, then the slope needs to be somewhere between those two, right? It's going to be between positive 1 and 0. So I'll just write small for sake of simplicity here. But we understand that it's in that range. I see this slope. Okay, it's going to be somewhere less than 1. I don't know, 0.2 or 0.4 or something. Like just approximately, we should know it's in that range. This blue one on the far left then, also positive. It's going upward. Should be quick to recognize. And if we calculated the exact slope, what kind of number would we get? So something big, something bigger than 1, 5, 10 or something. So right, big here. So this will be something larger than 1, exactly 1, less than 1, 0. And then just extending the same ideas, but just now with negative. So this will be a small negative number, somewhere between 0 and negative 1. And if this is exactly negative 1 and this goes past it, then this must be some large, big, very negative number there. So again, not necessarily knowing the exact numbers, but broadly speaking, positive or negative, big number, small number, that should be just right away something that we can recognize. So this is kind of the easier version of it, looking at this and recognizing that. So what we care about is with slopes on an actual line. So okay, so let's just do these ones again. Make sure we remember this here. What's the slope? 0, flat line. So slope 0. How about this one here?
Negative.
Negative. Give me an approximate number. Doesn't have to be perfect, just a best guess. It's -1 would be exactly this. This is less than that. Okay, -2/3 maybe. So around that range. All right. What about this one here? We can use the grid to help us a little bit, but again, I'm not looking for a super exact number, just your best guess. Okay, so positive or negative? Positive, bigger than 1. And I could also notice this would be a slope of 2. So it's a little less than that. So I don't know, 1.8 or something maybe. So positive, a little bit bigger than 1. This one down here. All right, so positive number. Three, I can actually notice on the grid, it looks like we're, if not exactly 3, we are very close to 3 with that one. Okay, so that's right. So we care about this with recognizing this on a curve. Each of these things are actually what we call tangent lines. A tangent line means we have a curve. We just choose some point on that curve. Choose some point on that curve, and we want to know what is the slope of the curve at that point. What's the slope at that point? Well, the way we do that is we draw a line, straight line that touches the curve at only one point. So draw this line like this, touches the curve only at that one spot. There is only one of these lines. There's only a single line that's possible to draw that will touch at one point. Any other slope would touch at least 2 points. So only touches at this one point. So that's a tangent line. And then just what's the slope of that line? What's the slope of the straight line? That's 0. Therefore, the slope of the curve at that same point is also 0. So just in your mind, you kind of draw this straight line here. That's how we recognize what the slope of the curve would be at that point. So same idea for all of these other ones. So let's try that here with some more points. Let's start with this one. In your mind, draw that tangent line and then give me an estimate for the slope. Okay, positive or negative first? Okay, is it kind of bigger than -1 or smaller than -1? Bigger? Or maybe just very close to -1? Yeah, okay. So m equals, if not exactly -1, looking at the grid, I think it's slightly more negative than that, but approximately -1. Right? That's pretty close to -1. Okay. This next one? 0. Okay, that should be a really easy one to recognize. So we would just get a perfectly flat line like that. So that slope looks like it's going to be 0. Again, we're just estimating. We have fancy tools that will let us calculate the exact slope at that point. For now, we're just doing visual, quick approximation. All right, 2 more. This one here. 0.3, so positive, and we're saying 0.3. So it's definitely less than 1. 0.3, yeah, that seems about right. Maybe a little more than that, but again, just a rough estimate. That's close enough for us. And one more here. Two or three. Okay, so positive, definitely more than 1. Again, 1 would be this perfectly 45-degree angle line. It's steeper than that. If I'm looking at the grid here, I notice this point and this point. So above, it's a slope of 4. Below, it's a slope of 3. So somewhere in between, I don't know, 3.5 maybe. There are more kind of tricks and strategies and stuff we can use to estimate these more closely. I'm not too worried about that stuff, but we should be able to recognize this. Positive, 0, negative, and also kind of bigger than 1 or smaller than 1, and also relative to -1. Okay, so do a bit more of that in the next class, but for now, let's switch over to the total revenue, total curves that I showed you. This whole process, we are getting ready to do calculus, differential calculus. So this is the thing we're working toward. This is kind of the definition, the core idea of what all of calculus is. So we'll get there soon, but not quite today. You're sad about that? Okay, we'll get there. Just a little bit of patience. Okay. So as I mentioned at the end of our last class, when we dealt with break-even points, we had our total cost line was very conveniently, very suspiciously, just perfectly straight. And our total revenue line also just perfectly straight, often not what happens in the real world. In your microeconomics class, I'm sure you've gotten to this point talking about demand curves and supply curves. And we call them curves because they're not straight lines, or basically never. They're always going to have some sort of curve pattern to them. So same thing happens with profits and revenue and cost equations. So that was the preview. I asked you to tell me why. So the first question I gave you here, again, just visually, if we can recognize it from the slope stuff that we just talked about, excuse me, where, give me the Q value, so the x-axis value, where the slope of this curve is 0 or closest to 0. Between 10 and 15, I think we can be a bit more precise. All right, we're saying 12. So imagine 12 up and about this point here. So again, if this is our thing and we draw a tangent line, so it looks like, yeah, around 12, that's going to be the spot where the slope is closest, or it will be exactly 0 at some point. Looks like it's about there. Okay, so that was the first part. Second part of this was, why does the total revenue graph here, why does it have this curve? So lots of people have mistakes in saying, well, like, where is it closest to 0? They were just trying to tell me the y value, or people thought that this was representing time. This is not time. This is if Q, so if we make a small number of things, our revenue is this much. If we make more things, our total revenue goes up. But if we sell even more things, our total revenue is going to go down somehow. How can that happen? Yeah. Okay, the exponent here, but okay, so that's how we make a math model to represent this. But I'm asking why, like in the business situation, what's happening with customers and whatever that causes this curve to happen?
Because of the elasticity of demand that keeps increasing.
Okay, and what's the thing that controls that elasticity?
The price.
Okay, price. If you're a customer in a store, there's something that you want or you need or whatever. You've made that decision. I want this thing, but are you going to buy it? You're going to look at the price. Is this a fair price for this product? Am I willing to pay this price for it? So short answer is if, all right, sorry, not the short answer. We'll spend a bit of time on this. So let's use iPhones, kind of what we did with the earlier break-even stuff. So the numbers on this chart are not going to match this. Just ignore that. So let's say this point here, this is how much this reflects the number of units that we will sell with kind of the ideal price. iPhones cost like $1,000 roughly. That's typically what the new ones cost. So let's say Apple, they've done their good math and whatever, and they figured out $1,000 is the perfect price to get the most total revenue. So let's start with that, where our price is 1,000. And let's imagine what would happen if the price was not 1,000, but the price was 10,000. What would happen to their sales? Okay, so very, very few people will buy it. So the money, the revenue per unit is way higher. It's 10 times as much, but there'll be more than 10 times fewer people buying it. So the result is the overall profits is going, oh, sorry, not profit, revenue. Overall revenue is going to be a lot lower because most people will say, that's just too much money. I could buy 2 cars for that much money. I could buy like 10 other phones for that much money. That's just crazy. I'm not going to do it. A few idiots or a few super rich people, sure, but most people will say, no thanks. So that makes sense on the left side, but what about on the right side? So let's say an iPhone costs $10, not 1,000, but $10. How many would you buy? At $1,000, you probably each just have one, right? You don't buy like 3 at the same time. If it costs $10, how many would you buy? Yeah, like you'd probably buy a few more. Hey, I'd buy like 2 or 3. Use one as an alarm clock, another one to like play music in my living room. I don't know, like if I have like a young, like a nephew, or just give them as like a toy to play with. Who cares? It's $10, right? So I would buy probably more than one, but I wouldn't buy 100. At some point, it doesn't matter how low your price is. People have bought all that they want and you can't sell them more because they just don't want any more of them. You've fully satisfied the demand. So that's when total revenue goes down because we're selling more, but we are earning a lot less money per unit. So there's some kind of perfect, nice, happy medium, this sweet spot here, where we get the highest possible total revenue. So short answer is price. Remember, total revenue is price times quantity. If we look at this equation here, we don't see price. We'll talk about how we use price to create this thing. So price is reflected in this. We just are not seeing the p-value there. So don't forget about price. Okay. The other thing with the total cost curve here, again, just looking at the slopes, where is the slope 0 or closest to 0? 70? 75? Anything there? I think a little lower, maybe around here. I guess around 60 is maybe a little bit lower of a slope, but roughly there. So we got the idea. So the slope is not 0. It never is going flat, but it does get close to that. That's the lowest slope. All right. So the harder question here, how does this happen? So it kind of makes sense that, so, well, first of all, total cost, when we make and we sell 0 things, we still have the starting cost, that's the fixed cost. And then if we sell more things, so we have a variable cost, so total cost is increasing. But as we go, we kind of get this efficiency here, right? The people, the workers are better trained, or they work faster, or whatever. And then we get to some point in the middle, and then so it gets more efficient, but then the cost starts going up, curving up again. How can this happen?
This economies of scale.
Sorry, say it one more time.
Taxation.
You guys are talking at the same time. Vincent, go ahead.
Well, I said this economies of scale.
Okay.
So, yeah.
That is our key term here. Can you give me a practical example? Like if we have a factory making cars or something, how could what is an example of diseconomies of scale?
Could be poor communication, for example, between the supervisor and the workers, maybe.
Okay.
Yeah, it's about the management stuff, because the company is getting too big and they're becoming inefficient because of that. So
Okay.
they're not meeting their targets, and so yeah, the costs will increase
Okay.
because of that.
So on the left side here, what is happening is called economies of scale. This is basically the efficiency thing. So if I have a factory and I have like 2 workers, well, each worker has to do kind of all the roles of the factory. But if I expand my production and now I have 100 people, well, each person can be more specialized. They get better at their job, where I can hire kind of experts or whatever. The machines are just kind of running all the time. Everyone knows their role better. It's just more efficiency from, if you do things kind of more, then you get better at it, basically. The other side is diseconomies of scale, where at some point you just get too big and it's too much of a mess, and things like you lose that efficiency because the organizing and the managing all that stuff just gets too hard. So again, yeah, like a supervisor, can they really observe what everyone is doing and know? Maybe we have a worker who's secretly just like hiding behind the machines and playing games on their phone, but nobody noticed because we can't observe them. Or maybe we are, at this point, we have all of our workers kind of working like 8-hour shifts, and that's great. But then if we want to push our production here, we have to start paying them overtime. So now our labor costs are going up. Or we ran out of like the local supply of steel or glass or something. We have to order from some other supplier far away and pay more in shipping costs, material costs go up. All kinds of things like that can happen. If we try to push beyond this point, we get inefficiencies and lots of things like that can happen. So that's kind of why we get more efficiency up to a point, but then it gets too big and we get less efficient afterward. So the point that we really care about, if we're trying to optimize our cost, is this point here where the slope is the lowest possible. It's not 0, but lowest possible. So our calculus tools will help us very easily find a maximum of a curve like this. And then for this kind of curve, we just do one extra kind of layer of our calculus stuff, and then we can find these points too. So this is how these curves can happen, why these points are important, and then we'll see we'll take a bit of time to get there, but we'll see how calculus will very easily give us that information. By the way, this kind of curve, this is a cubic. So it's a something cube, the variable cube is giving this kind of pattern. All right, that's where we are going on the next slide. So we need kind of a collection of tools to be able to get ready to talk about those more realistic cost and profit and revenue equations and do some calculations with them. So nonlinear functions, we should have a basic understanding of how these work. So far, everything that we were talking about was a linear function. So straight lines, this. But of course, that doesn't always happen. So one kind of curved function like this would be what we call a quadratic. So it's just something squared. So ax squared plus bx plus c, something like this. Another kind is a cubic. So something x cubed plus something x squared plus something x plus something. And these can all continue on for whatever x to the exponent 4 and 5 and 6 and 7. Lots of those. These are called polynomial functions. Polynomial. Poly means many. Nomial, that just means that each of the parts. So cubic function has 4 different parts that we're adding together to produce that function. So polynomials. There are a few other types which we will not be using in this class, but definitely come up often, and you'll see later if you haven't already. Exponential functions, where the variable is in the exponent. The other ones, it was x squared, so it was x to some exponent. But here, the variable is in the exponent. That gives us functions that look like this, very shallow on one side and then just very quickly rise on the other. I mentioned logarithms briefly, where we have kind of the opposite pattern. It's basically the complement of these exponential ones. And then there's also hyperbolic, which look a little weird, but they end up having a bunch of applications, where the graph would just get very, very close to the axes, but never touch them. So these happen when we have 1 over the variable. So 1 over x or 1 over x squared or 5 over x or something like that. So those give us those hyperbolic patterns. We're not really going to talk about these, but good to know that these exist. Okay, so let's actually talk about these. If you've done like graphing and stuff with like an x squared or an x cubed or whatever, this is going to feel pretty simple in review. We're not going to spend too much time on this, but we do need to have just a kind of general understanding of what these graphs look like and how we manipulate them. Okay, so let's pretend we have no idea what this thing looks like. How can we draw this? Okay, table of values. So if we don't know what it looks like, we can't just draw the shape. We have to figure it out. So x and f of x, or this is the exact same thing as just saying y equals x squared. Okay, so table of values, let's say, well, -2, -1, 0, 1, 2. Okay, and we just calculate what the other values are. So when x is 0, x squared, that's just 0. When x is 1, x squared is 1, or y is 1. When x is 2, it's 4. Okay, we see that pattern. On the negative side, if it's -1 and we square it, then we get +1. And if we have -2, we square that, we get +4. Okay, that should be enough for us to kind of see the patterns that are happening here. So 0, 0, 1, 1, 2, 4. 3, 9 is going to be another one. -1, 1, -2, 4, -3, 9. And we just connect the points like that. So that's approximately what the curve looks like. So anytime we have a function we don't know, table of values will give you a visual sense of what it looks like. We can always jump to that. There are kind of deeper patterns and things we could recognize, but we're not going to talk too much about that. So again, this is y = x². We'll talk about 3 different ways of manipulating this to make sure we understand what happens when we change things about it. So these 3 things down here. Okay, so on the left version first, if this thing here is our y = x², or f of x is x², and then we change it to be x² plus 3. What's going to happen to this graph? Okay, move up by 3. So all the points, can we kind of slide the whole thing up by 3? So like this point, 0, 0, so that it becomes 0 plus 3. Okay, and then 1 squared is 1 plus 3. So there, 2 squared is 4 plus 3, 7, etc. And same thing on the other side. So it would look like this. The shape is the exact same. The only thing that's happening is the whole thing just slides up. And what about the other one, x² minus 3? All right, we just slide the whole thing down. So there, and 9 there. All right, and we get this shape. Exact same shape, just sliding it up or sliding it down. So that's the constant term, the final thing with no x in it, that will just slide up or down. Next one. So now we have an ax². So the a term is the coefficient, and now it's a 3x². What's going to happen with this graph? Okay, so it's going to look like it gets thinner. So visually, that is what's happening. Mathematically, what's actually happening, it's a vertical stretch. The whole thing is just getting kind of stretched up and down. So 1, 1, sorry, 0, 0, 1, 3, 2 squared is 4, but then times 3, that's 12. That's already off our graph. So very like this. So it looks like the 2 sides are just kind of getting squeezed together or closing. Again, mathematically, it's a vertical stretch. And then on the other side, 1/3x², opposite. So it's going to look like it's sort of opening up. Again, actually, it's a vertical compression. Everything's getting squeezed down. So 1, 1, but then divide by 3, so 0.3. 4, but then divide by 3, it's 1.3 here. 3 squared, 9, divide by 3, that's 3. And on the other side, so we're going to get this kind of pattern here. That side's a little wrong. Okay, so the coefficient at the front, if it's a number that's larger than 1, it sort of stretches everything vertically. If it's a number that's less than 1, it sort of compresses everything. The last one, if we now have our a term is just -1. Okay, the whole thing is just going to flip upside down like this. I don't know why that is. What? No. Okay. Inputs. This one. TMI. Okay. All right. We had some little fun here in the classroom, but that's solved. So there are more ways that these can be manipulated and things that they could be flipped in different directions and stuff. I'm not going to worry too much about that, but these three types, which I have summarized here. So if our C value, again, with this version, the standard form, 8x squared plus bx plus c. If the C value is positive, the whole thing just gets shifted upward, slides upward. If it's negative, it goes down. Absolute value of A is larger, then everything gets steeper. And if it's decreasing, then it will become less steep. And if the sign on A, if it's positive, the thing is going to be kind of opening upward. And if it's negative, it's going to be pointing downward. So those are the three things. And any one of these things, if we want to graph it, just a table of values will help us figure that out. Okay, so this is kind of the simplest kind of polynomial function, an x squared, but we can have more. Oh, I remember, right, x cubed is a little later. Okay, so let's talk about slopes here and just sort of what's happening. Again, this visual identification of slopes. So where on this graph, tell me a spot where you see a negative slope. Negative slopes.
Left side.
Three, sort of kind of the left side. That's the easy way of saying it. So everything on the left here, this is a negative slope. Negative, 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 negative. And on the right side, positive slopes. It's all pointing upward. These are all positive slopes. And what is happening at exactly x equals 3? 0. Our slope is 0 there, which again, we can have our sort of tangent line thing and say, well, that slope looks like it's 0. So at that point, the slope should be exactly 0. But also, if they're negative on one side and positive on the other side, it must go past 0 to become positive. So there has to be some spot where the slope is 0 like that. Okay. So a point like that where x equals 3 is what we call a turning point for our function. So turning point is where the function turns, it changes direction. So here on the left side, it's going downward. Slopes are all negative, but then it turns, and now all the slopes are positive, and it's going up. So turning point. We can also have the reverse pattern. It goes up and then it goes down. So the first type we call a minimum point because it's a minimum point. That just makes sense. So slopes are going from decreasing to increasing, from negative to positive slope. And we can have two kinds of minimums, either just a local minimum in the immediate kind of nearby area. It's just a minimum there, or it could be a global minimum for the whole function. And then exact same thing on the other side, like this, where we have a maximum point because it's the highest point of the graph in that region. Sort of changing from positive slopes to negative slopes. All right, that's just the basic idea of turning points. Okay, so let's try to graph a slightly more complicated function here, something like this, x cubed. So same thing, we can make a table of values, our x and f of x. So say -2, -1, 0, 1, 2. So 0 cubed is just 0, 1 cubed is 1, 2 cubed, 8. -1 cubed, -1, -2 cubed, -8. Okay. So with our x squared, the y values were all positive because we were squaring it. But this one's going to be different. So on the left side, 1, 1, 2, 8 is already off our graph. So here somewhere, and 1, 1, and down here off our graph. So the left side is going to look like this, kind of like the x squared, but just steeper. But then the right side and the left side is instead going to go down like this. That's not a great drawing. Should look like this here. Okay, so let's think about this and then kind of the whole turning point idea here. Where do you see positive slopes on this function? Okay, so on the left side here, positive, 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 positive. On the right side. What about on the left side? These are negatives. Okay, the y values are negative. The y values here are all negative, but the graph is increasing. These are all positive slopes. Again, think of these tangent lines. These are all positive slopes. Positive, 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 positive. So fancy terms here, we'll call them, so it's an interval of increase because the graph is increasing, moving upward. So where slope is positive. What is happening exactly when x is equal to 0? Do we have a turning point? No, why not? Okay, so turning point means it has to turn. The slopes have to actually change from positive to negative, negative to positive. It's not turning, we don't have a turning point. What's actually happening here is that the slope does go perfectly flat to 0, but then it starts going positive again. So it kind of tricks us. It looks like it's going to turn, but then it doesn't, and it just keeps going the same way it was going before. So this is kind of a special case with a cubic like this, and that's exactly x cubed. More generally, they look like this. This is a more kind of traditional shape for a cubic function. This one is x cubed minus x squared minus x, and we get this shape. So now we can kind of have a more meaningful discussion, slopes and these turning points. So where do we see intervals of increase or decrease? Where do we see positive slopes, negative slopes? You said -0.3 to there. All of these are positive slopes? No. Okay, so we can recognize on the far left side, these are all is very positive here. So positive, 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 positive. So the graph is increasing. Then something happens, and now the graph is negative. It's decreasing between these two lines here, and then it is increasing afterwards. Slopes are all positive. So we have this kind of up, down, up. 1, 2, 3, x cubed. So that gives us a sense of what would happen there. So this is the pattern that we can see. Where do we have turning points? Okay, so these lines, that's exactly what the lines are. If your function is changing at some point, okay, well, those are what the turning points are going to be. This one is obviously x equals 1. This one is like negative 0.4 or 0.3 or something. Okay, so we can see the slope patterns where it's increasing and decreasing, and we can also see these turning points here. One more thing that we should talk about with these functions, not about slopes, but just about the appearance of them in general, zeros. What are the zeros of this function, if anyone knows? Points where not the x values. Or sorry, okay. So the zeros are basically the x-intercepts. Any spot where the y value is 0. So what x values give us the y of 0? How many zeros do you see in this function? 3. So 1, 2, 3. If we have the graph, it's very easy. You just look, where does it cross the x-axis? Those are the zeros. So this point looks like it's about x equals negative, or sorry, positive 1.7 or something. This is obviously exactly 0. This one, I don't know, negative 0.6 roughly. We have this thing. We could calculate them exactly, but just we can look at the graph and see it as well. So zeros are just the places where your function is crossing the x-axis. So x-intercepts basically. So this is the formal definition of this. So zeros, x-intercepts, any x value that makes the y value equal to 0, the f of x equal to 0. So there could be potentially many, like if we have just a straight line, obviously we're just going to have one of these points where it's going to cross that axis. But if we have a curved function, we can have lots of them. If we have a function that's x to the exponent n, then there could be as many as n turning points. There could be none, but there could be up to that many. And we have lots of ways of finding them. We can just look at a graph, or we can take the equation and do some factoring. There's a sum product method. If we have an a coefficient, you, I'm sure, have all learned the quadratic formula way back in school. We'll ask you to remember, or I'll ask you to remember what that is in our next class. Rewriting standard form. So there's lots of ways of figuring this out, but we just want to know where those x-intercepts are. It might seem pretty kind of simple or trivial when we're looking at a function like this, but it turns out if we find a derivative and find the zeros of that, that is what's going to find the maximum and minimum points for us very conveniently. Okay. I don't know, like usual, went way faster with you guys. So this is as far as the other classes got. Let me just see what else we have. Right. So the next thing is actually doing it and this quadratic formula or whatever. So more complex functions, curves, talking about maximum minimums, and a little more kind of visual recognizing stuff, visual stuff. Okay, the rest of that we'll come back to next time. So at this point, so far, we should be able to visually recognize, well, first of all, slopes, also zeros. So just where does your function cross the x-axis? Pretty simple. Where do you have maximums and minimums? Just because you have a turning point there. And by understanding the slopes, by being able to visually just recognize what a slope is, we can see here's where the graph is going up, here's where it's going down, here's where it's going up. It's going up by a lot, going up by a little bit, so we can make an estimate of those slopes. The second part is what we will get to next time. If you want to do some more reading about this or review the practice questions I posted on our classroom page, from this point, everything we are going to do is from this textbook. It's also one of those OpenStax textbooks. It's free. Just go download the PDF, whatever. There's a link to it on our classroom page. But the intermediate algebra textbook we've been using so far doesn't really have much of a discussion of these functions. So from this point on, we are doing everything from this pre-calculus textbook. Right, so more about polynomial functions and recognizing them.